Okay, let's just dive right into this. We absolutely all know that sinking feeling, right? You're cruising along, making fantastic time, and then, boom, you're staring at an endless glowing sea of red brake lights. Traffic. Literally the ultimate everyday frustration. But then you glance down at your phone, and somehow, your navigation app already knew it was there. Welcome to this explainer, where today we're skipping the usual intro to get right into the fascinating, totally invisible machinery that roots our daily lives. We're looking at exactly how Google Maps calculates your commute.
Seriously, how does Google Maps know about a traffic jam before it even happens? It kind of feels like magic. You punch in an address, hit start, and in milliseconds, this incredibly complex web of predictions just pops up on your screen. But spoiler alert, it's not magic. It is a wildly sophisticated blend of live data, historical patterns, and absolutely bleeding-edge artificial intelligence.
And honestly, this brings up a situation I think we've all found ourselves in. Someone actually shared this exact anecdote in our source material, saying, "I ignored the new route. Bad call. Within minutes, I hit a massive traffic jam." So why do we do that? Why do we think we know better than the app? Usually, it's just because the road right in front of our windshield looks perfectly clear. Well, today, we're going to peel back the layers of this onion to figure out why ignoring that reroute is usually a terrible idea and what exactly the system is seeing that you aren't.
What's really mind-blowing here is just the sheer, ridiculous scale of the operation. We're talking over 1 billion kilometers driven with Google Maps every single day, across more than 220 countries and territories. To put that into perspective for a second, that is literally like driving to the sun and back, multiple times a day. Managing routing at that massive scale means the platform has to track an unimaginable number of moving parts every single second.
So you're probably wondering, where does all this data actually come from? Well, it comes from us. The exact second you open Maps, your phone basically joins this massive, real-time, passive data collection network. It starts sending anonymous smartphone telemetry straight back to the system. We're talking 3 key things. Step 1, your GPS location. Step 2, your speed. And Step 3, your heading. Picture millions of phones constantly beaming these tiny little packets of data. If cars on a highway are cruising at normal speeds, boom, the road is clear. But if thousands of devices suddenly slow down all at once, the system instantly flags a bottleneck.
But here's the thing. Raw speed data isn't always enough to explain why something is happening out there. To build a truly complete picture, Google relies heavily on human reporting and real-world city context. Through Waze, which Google acquired, drivers are manually reporting accidents, debris on the road, or sudden closures. Then they layer in authoritative government data. Think speed limits, toll roads, active construction zones. They even track events. So if there's a massive marathon shutting down streets or a stadium concert letting out, the algorithm already has the on-the-ground context to expect a huge, sudden surge in cars.
Okay, so here is a crucial point. Live traffic conditions, they really only give you a snapshot of right now. If your drive is 45 minutes long, what actually matters is what the road is going to look like 45 minutes from now. To figure that out, Google Maps compares live conditions against incredibly deep historical patterns. The system analyzes traffic in tight, 10-minute intervals over years and years of data. This lets the system build these ridiculously precise baselines of how a specific stretch of road behaves at any given minute of the day.
Let's look at the 280 freeway in Northern California as a perfect real-world example of this. The historical data there shows a crystal-clear pattern. Vehicles typically travel at a breezy 65 miles per hour between 6 and 7 a.m., but roll around to the late afternoon, that speed just plummets to like 15 or 20 miles per hour. By establishing exactly what normal looks like, these predictive models know precisely when rush hour is going to start, when it peaks, and when it finally fades away.
But as we all know, normal can literally change overnight. Pre-2020, Google relied on years of historical data. Then early 2020 hit. Lockdowns caused up to a 50% decrease in worldwide traffic. Suddenly, all those years of historical patterns? Completely useless. So to adapt, Google completely updated its models to become hyper-agile. Fast forward to today, and the system automatically prioritizes historical traffic patterns from just the last 2 to 4 weeks, pretty much completely ignoring anything older than that. This keeps the predictions razor-sharp, even as global commuting habits constantly shift.
Which brings us to the ultimate challenge. What happens if the jam hasn't even formed yet? Like, what if you're 30 minutes away from a highway merge that is perfectly clear right this second, but is absolutely going to be a total parking lot by the time you actually get there? To peel back this final layer, we got to look at the core artificial intelligence driving the whole platform.
Now, I want to slow down here for just a second because this is really the technical climax of how all of this works. Google partnered up with DeepMind, their AI research lab, to implement something called graph neural networks, or GNNs. A GNN is a generalized machine learning architecture that basically conducts spatio-temporal reasoning. Right? What does that mean in plain English? It means it allows the AI to actually understand the physical connectivity of real-world road networks. It's not just looking at one isolated road. It's looking at how every single road interacts with the roads touching it over both space and time.
Let's actually walk through how the AI maps our physical world into a mathematical structure. First off, it divides the world's roads into these things called supersegments, basically dynamic blocks of adjacent roads that share traffic volume. It treats each physical route segment as a node and the intersections connecting them as edges. By linking these nodes and edges together, the AI can actually predict spillover delays across multiple intersections. It inherently understands that a delay at a left turn up ahead is eventually going to back up right into the lane you're currently sitting in. The best way to think about these nodes and edges is like a giant, complex plumbing system. Traffic flows through these road networks exactly like fluid flows through pipes. If a tiny side street gets blocked up, all that pressure has to go somewhere, right? So the jam spills over into the main highway. Graph neural networks are so incredibly powerful because they can calculate the dynamics of this fluid propagation, anticipating that miserable stop-and-go traffic before the bottleneck even fully materializes.
Now, processing millions of these dynamically sized supersegments created a massive computing challenge. Basically, the models were becoming unstable during training. To fix this, DeepMind utilized a really clever reinforcement learning technique called metagradients. Essentially, when you're training an AI, you have a learning rate, which dictates how plastic or adaptable the system is to new information. Metagradients allowed the system to dynamically learn its own optimal learning rate schedule entirely on the fly. It literally taught the AI how to teach itself, stabilizing all those massive variations in the road graphs and making it robust enough for global production.
So, what is the grand result of layering anonymous telemetry, 10-minute historical intervals, authoritative data, and DeepMind's fluid calculating graph neural networks? It's this massive number right here, 97%. Despite all the totally unpredictable variables in the real world, crazy weather, accidents, sudden closures, Google Maps ETA predictions are consistently accurate for over 97% of trips globally. Honestly, that is just a staggering engineering achievement.
And the direct impact of that DeepMind GNN partnership was practically immediate. By implementing this advanced AI, Google Maps drastically reduced their already super low rate of inaccurate ETAs. We are looking at up to a 50% reduction in ETA errors in major cities like Taichung and Berlin, and over a 40% reduction in Sydney. They took a system that was already highly accurate and made it exponentially smarter at predicting the future.
Finally, let's bring this whole journey back up to the surface layer, the screen, right there on your phone. Billions of data points, dynamic supersegments, and spatiotemporal AI predictions are all ultimately distilled into the incredibly simple color threshold system that we rely on every single day. Green means traffic is flowing freely, yellow means vehicles are starting to slow down, and red means gridlock and severe delays. It takes just an immense amount of back-end complexity to create a front-end experience that is this simple, intuitive, and frictionless.
Which leaves us with one final thought to ponder. Next time you see a red line light up on your route, and the app tells you to turn down some strange, random side street, will you trust the algorithm or your own instincts? Considering the billions of data points and predictive AI working behind the scenes just to save you a few minutes, you might just want to take the detour. Thanks for joining this explainer, and we'll see you next time as we continue making the complex entirely clear.